Here in this problem, as we try to arrange this structure into its most stable chair conformation, we need to keep in mind two main principles of drawing cyclohexanes in their chair conformation. One is that we look for larger, bulky substituents on the cyclohexane ring. If we see any of those, we know that those are more likely to be equatorial than axial. But for the molecule that's given here, we don't have to worry about the size of any of the groups because all 8 substituents on this cyclohexane ring are methyl groups, so they're all the same. So what our goal is instead to get as many of the substituents into equatorial conformations as possible. So just for clarity, I'm going to mark this carbon as carbon 1 and start with it down there. At our first carbon, we have methyl groups pointing both up as well as down. Now if I continue around the ring this way, our second carbon has a methyl group pointing up, third carbon points down, the fourth carbon, the methyl points up, fifth carbon it points down, and carbon 6 has both again. Now what we can see in this conformation is I have a total of 6 axial and 2 equatorial. So that's not likely to be a very good conformation. Again, remember, we want as many of them to be equatorial as possible. So instead now, I'm going to try again, and I'm going to make this carbon number 1. Again, carbon 1 has 2 methyl groups. Carbon 2 points up, carbon 3 down, carbon 4 is up, carbon 5 is down, and carbon 6 has both. In this second conformation, I now have 6 equatorial and 2 axial. With significantly more groups in an equatorial conformation, this second structure is definitely our more stable chair conformation.